In the last video, we talked about the idea that the universe is expanding, and we looked at some of the properties that such an expanding universe would have. But one of the things that we have to ask is, what observable effects would this expansion have? Like, what physical evidence do we have that the universe is actually expanding? Because no matter how good our theory is, if we don't have any evidence to back it up, well, it's not much of a theory. Well, it turns out that there's actually very strong evidence for the expansion of the universe, and a lot of it comes from the idea of cosmological redshift. So, cosmological redshift. And this is essentially the effect that the expansion of the universe has on a beam of light that's moving through the universe. So let's say we start out with the universe at some time, and let's say I have some source of light over here, and we're going to be sitting over here with our telescope waiting to see the light coming from this source. So this source is going to emit some light, and that light is going to have a certain wavelength. So we're going to call that wavelength lambda e, the wavelength of the light when it was emitted. Now, as we wait, this beam of light is going to propagate across our universe, but as this light propagates, the universe is actually going to expand. And as the universe expands, so here's my source now, and here's where I am now. The universe has expanded a little bit, and this light has been stretched out a small amount. The wavelength of the light is now longer than it was when we actually started. So as the universe continues to expand, and this beam of light continues to move across our universe, so here's the source and here's where we are, when it finally reaches us, the wavelength of the light is going to be significantly longer than when it was emitted. So we're going to call this lambda O, the wavelength of the light when we actually see the light hit our telescope. Now, I've said that as the beam of light moves across the universe has expanded, but a good way of quantifying how much the universe has expanded is to introduce something known as the scale factor, which we denote by the letter A. So A is going to be our scale factor, and it's simply a measure of how much the universe has expanded. So let's say at some early point in our universe, when the light was emitted, we have a scale factor of AE, the scale factor when the light was emitted. And then finally, when that beam of light was actually observed, we're going to say our scale factor is A0. So we can, let's say we arbitrarily set this value to 1. So the scale factor of the universe right now is 1. And maybe when the beam of light was emitted, the scale factor was only 0.5. And that means that during this time, the universe effectively doubled in size due to expansion. Or if I said that instead of 0.5, let's say I said the scale factor of the universe was 0.1, then the size of the universe would have increased by a factor of 10, because 0.1 goes into 1 10 times. So we have this idea of a scale factor. And we find that we can relate the change in the wavelength of the light to how much the scale factor has changed. And it's a very simple formula. The wavelength of the light we observe over the wavelength of the light that was emitted is equal to the scale factor when we observed light over the scale factor when the light was emitted. So if my universe expanded by a factor of 10, so if this is 10, then the wavelength of the light is also going to get longer by a factor of 10. Now there's another way that we can also kind of characterize how much this wavelength has expanded, and that's by introducing the concept of a redshift. So redshift we denote by the letter Z, so this is redshift. And this is defined to be the wavelength of the light that we observe minus the wavelength of the light that was emitted over the wavelength of the light that was emitted. So it's kind of a fractional change in how much our wavelength has changed. So this is what we often want to measure when we're looking at distant objects. However, we might say that, well, I can see at my telescope what the wavelength of light is. I can, easily measure that because that's what's actually at my telescope. But how do I know what the wavelength of light is that was sent from whatever distant source I have? Well, if I look at the spectrum of the light that is arriving at my telescope, then I know that specific chemicals like hydrogen and helium will show very, very particular spectral lines in the light that is arriving at my telescope. And if I notice that all of these lines are shifted, so I would observe this, so this is what I observe and this is what was sent or emitted, then if I notice that all of those wavelengths are shifted by a certain amount, I can actually calculate what the redshift is, and I can actually calculate this very accurately. So I recommend looking at the video on spectral lines if you want to kind of learn a little bit more about this. But now if I take this redshift and multiply it by the speed of light, c, so I multiply this by c, this will actually equal the velocity that my source is moving away from me at due to the expansion of the universe. And if you've seen the video on Doppler shift, then you'll recognize this equation. So I now have a way of measuring how fast this object is moving away from me. And going back to the last video, the final step is we can relate this velocity to the expansion of our universe. So it's Hubble's law tells us that the velocity that an object is moving away at is equal to the Hubble parameter times the distance that this object is away. So if my equation, if my idea that the universe is expanding is correct, if I plot the velocity of these distant galaxies against the distance that they are away, I should find that it gives me a straight line. And if we actually look at some data, then we get something that looks like this. Now this graph, each of these points represents an individual galaxy, and for each of these galaxies we've measured the redshift using the technique that I mentioned up here. So we know how fast it's moving away from us in kilometers per second. And we've also measured the distance to these galaxies in megaparsecs. And just for a sense of scale, 1 megaparsec is 10 to the 6 is 10 million parsecs. And a parsec is equal to about 3.26 light years. So when we're talking about distances 10 or 20 megaparsecs away, we're talking about tens of millions of light years away. So that gives you a sense that these are very distant objects that we're looking at. And what we notice is that we do get a straight line for our velocity versus distance graph, and the slope of this line is actually the Hubble parameter. And right now, the best estimate for the Hubble parameter is about 70.4 plus or minus 1.4, so this kind of gives you a sense of how unsure we are of this number. It's 70.4 plus or minus this amount. And the units are kilometers per second per megaparsec. So they're a little bit strange units, but what it means is if I'm 1 megaparsec away, so if I'm just a small distance away from my observing point, then that galaxy will be moving at about 70 kilometers per second. So if I'm 10 megaparsecs away, if I'm this distant away from the galaxy, then that galaxy is moving away from me at about 700 kilometers per second. So this gives us a good idea of what the expansion of the universe is actually doing, the rate that it's expanding at. And we can actually relate this value to the scale factor that we were talking about before. The scale factor, of course, corresponding to how much the universe has expanded. And this Hubble parameter actually corresponds to the derivative of A. So this dot just means rate of change of. That dot means rate of change. So it's how fast the scale factor is changing over the scale factor itself. So this gives us a sense of how fast is the universe expanding at, and right now it's at this value. Now there are a couple of other things that I just want to point out before we finish here. First off, when we talk about speeds like 70 kilometers per second, in everyday terms, that seems like an incredibly fast speed. But when we consider things like the orbit of the Earth around the Sun, the Earth is orbiting the Sun at around 30 kilometers per second. And I think that Mercury is going close to 50 kilometers per second. So when we're looking at objects that are very close to us, even though we say they're moving at, even at 1 megaparsec, we're saying it's moving at 70 kilometers per second, compared to other astrophysical motions, that's not really that fast. It's only when we get significantly farther away into the tens and hundreds of megaparsecs that we really get very fast expansions, very fast velocities due to the expansion of the universe. And there's something else that I want to point out with this graph. We notice that around 15 megaparsecs, we have this big clump of galaxies. Some that are going faster than we expect them to be, some that are going slower than we expect them to be. And this clump of galaxies actually corresponds to a cluster of galaxies known as the Virgo Cluster. Virgo Cluster. And I actually have a picture of the Virgo Cluster right here. So we see this group of galaxies actually corresponds to a number of these galaxies, and they're all interacting with each other. And one thing that's important to note is that these galaxies are all going to be orbiting each other. So maybe this galaxy here is orbiting in this direction. Maybe this galaxy here is orbiting in this direction. Maybe some of these galaxies are coming towards us, and other of these galaxies are moving away from us as they orbit the center of this cluster of galaxies. Now, those different types of motion will still show up in this redshift diagram. The galaxies that are coming towards us, well, they won't seem to be receding as fast because part of their motion is coming towards us, even as the universe expands away. And galaxies that are orbiting this cluster of galaxies away from us, well, they'll seem to be receding faster. But we notice that overall, in this entire cluster of galaxies, the cluster itself seems to be moving away at about the rate that Hubble's law would predict. So even though the universe is expanding, it doesn't mean that that's the only motion that these galaxies have. They can be orbiting each other, and that will show up in these diagrams as a little bit of spread around this line that we would expect. So we have the motion due to the expansion of the universe, and if there are a little bit farther off of these lines, then these galaxies might have their own peculiar motions, or motions that can't be accounted for due to the expansion of the universe. But as we get farther away, we notice that these differences in motion become very small compared to the motions that are just due to the expansion of the universe. But that's just something I wanted to point out, and if we're very close, well, obviously for the Earth orbiting the Sun, we're so close that we don't even notice the expansion of the universe. It's all just the motion of the Earth around the Sun that is the dominant effect. But that's just something I wanted to point out. So it's not all the expansion of the universe, but as we get farther out, that becomes the dominant effect. And we're going to talk about how this expansion of the universe, this rate of the expansion of the universe, can change in the next video.